Did it show up? Okay, here it is. This fitness function WI is an assumption. This is an assumption, right? So it's not, we basically sort of, that's like a primitive of the model that we assume the world is like that, right? We don't derive that equation, basically. We just sort of posit that, so that the world is such that, you know, there's two genotypes. One of them is cooperator, they give out the benefit B, and one of them is defector, where they don't give out the benefit B, and the cooperators also pay a cost. Okay, so so that's a fundamental different way of thinking about fitness than in the whole derivation of the price equation, where fitness was actually the realized number of descendants, right? Here, fitness is assumed to a model, assumed to be a function of your phenotype and your partner's phenotype, and in this case, it's sort of a deterministic function, basically, like depending on your phenotype and your partner's phenotype, you have exactly a given fitness, okay, and by assumption, okay. So, any more questions about this? Okay, so I'm gonna do one more thing, and we probably won't have too much time to go into. Well, we'll see. Actually, no, I'm not gonna do that. Given our time constraints, we only have 50 minutes or so. I'm gonna now. So I was gonna do multi-level selection. Sort of what's sometimes called the multi-level selection partition, or a multi-level selection partition of the price equation. But instead of doing that, I think I want to spend the remaining time on doing sort of a little bit more game theory and non-additive interactions. Okay.
Sorry, Erol, just before Matt John has just another comment. Do you mind before going into another topic answering that? Thank you.
Okay, yes. Can we say that the fact that transmission bias is not being zero in natural systems is a material of speciation? I mean, speciation in the sense of species splitting into two. I don't know. I mean, I think I don't know if that's actually necessarily related to speciation. It's possible that environmental transmission bias will go into speciation, but I don't see I don't see what the relationship is immediately. So variation within random points doesn't lead to population of mirror variety in genetics. So if the phenotype is exactly equal to the genotype, right, then any phenotypic variation has to be genotypic variation by definition, right? But of course, we know most phenotypes are not purely genetically determined. They're not exactly equal to some sort of, genetically transmitted material, or they're not exactly equal to genotype. There's some effect of the environment. So as the environment changes, phenotypes will change, and that can actually, I do think that it is very easy to write models or think about circumstances where sort of an environmental change can lead to speciation or can lead to sort of reproductive isolation, for example, which what most people mean by speciation. So like if you're, for example, if you're a herbivore living on a particular plant, like if you're a caterpillar living on a particular plant, if the phenology of the plant changes and with the environment, and therefore the emergent states of some caterpillars or some butterflies from pupae changes with that, then that might actually lead to like changes in the that might actually lead to reproductive isolation. But it is not so much. I mean, but that's like you have to like take it. I mean, you can't write those equations with the price equation, but you have to like actually specify what type of environmental changes taking place and how is that affecting, how is that interacting with the genotypes, and how is that interacting with the with fitness. So that's like requires a lot of steps to be written down. But this all can be expressed by price equation. I actually don't know if anybody has done it, but it can be done. People have done one thing that I can say. People have done to use the price equation to partition change into genetic change, phenotypic plasticity, environmental change, and so on. And actually, sort of one of the CompEcoEvo members, Arpa Tözgül, has published several papers using sort of long-term data sets from marmots and I think Sankilla sheep to partition change in using price equation, using a version of the price equation developed by Tuljaporkar and Coulson to partition change into different sort of environmental and genetic components. Okay. Okay, good, great. So, so what I want to do next is do some game theory, and I'm going to introduce game theory by sort of a slightly sort of kind of a jargony term of non-additive interactions. Okay. So additive interactions, like I said, are interactions where you can write down the fitness as sort of some function of the phenotype of your partner, okay, and plus some function of the phenotype of yourself, basically of your own phenotype, okay. So and in this case, both of these functions are linear, right? This is a constant times phi j and constant times phi I, so that's a linear function. In general, these could be non-linear, right? And it still will be additive. Okay, so additive and non-linear are slightly different things. Okay, and in a non-additive interaction, fitness is going to be a function of not just, you can't just write down as separate functions of your phenotype or some of the separate functions of your phenotype and others' phenotype only. Okay, and in the context of the sort of this donation game is again, so I'm going to call these genotypes now because that's the easiest sort of thing then, because we can ignore all this transmission bias term. There's a lot of interesting stuff going on with the transmission bias term. I don't mean to suggest that the transmission bias term is uninteresting or it's just a new sort of nuisance term, but it is sort of a lot more subtle. So you can probably teach more advanced classes on that. But so it is convenient to ignore, right? But that doesn't mean that you should be ignoring it in real world, right? But I'm going to ignore it anyway. So just because this is sort of the introduction to all of these things. So what we had before was this thing, right? So we had these two genotypes, 1 and 0, and then we could write down the additive fitness function. Why did I do that? I didn't mean to do that. We can write down the additive fitness function. So this was 1 plus b, this was 1 minus c, okay, and this is 1 plus b minus c, okay. So if I leave it at that, this is still additive, right? But I'm gonna just destroy all of that and add a d here, okay. So now I cannot write this fitness function like I wrote it before, right? So I cannot write this table as a fitness function. That's only a function of phi j plus only a function of phi I, because if I do that, I'm left with this d that only accrues, that this guy only gets if both its genotype is 1 and its partner's genotype is also 1, okay? So this d is very specially only obtained in this upper left corner, okay? So that means, so now, but I can still write down wi as a sum. It's just that now the sum has to be, so I get the phi j times b, and then minus c times phi I, okay, because those are still here, right? Use this phi I. If phi I is 1, you still get minus c, and if phi j is 1, you still get plus b, okay? But now if both phi I and phi j is 1, you get that additional d, okay? So then I can write that as plus d times phi I times phi j, okay? And obviously, this is only going to be 1 if both phi I and phi j are 1, right? So, so this d sometimes is called the synergism coefficient, or sort of non-additive interaction. And it can be positive or negative, right? If it's positive, that means that if both individuals are cooperators, they get something extra, right? It's synergistic. But it can also be negative, which means that if both of them are cooperators, they get actually less than b minus c, right? They each get less than b minus c. And so that so that's sometimes called as anti-synergism. And synergism if positive, or anti-synergism if negative. Okay. So, and we're gonna see that depending on the sign of that, you're gonna get positive or negative frequency dependence. Okay. Okay, so right. So so now we can do basically what we did before, right? We can basically take this WI and then plug in to our price equation, just as we did here, right? Okay. Again, the transmission bias term will vanish. So we're going to just get, because we were assuming the phi's are now genotype and there's no transmission. So that's actually like, that's a built-in assumption, right? In all of these things. So we can do, W bar times delta phi bar is covariance of Wi phi I. Okay, and then we can write down that covariance, write out that covariance. So this one will just vanish. Covariance of anything with 1 is 0. And then we'll get B times the covariance of phi j, phi I, minus C times the covariance of phi I, which is the variance of phi I. And then now we have this D times covariance of phi I, phi j times phi I times phi j with phi I. Okay. And this is the variance as before, right? So we can again factor out the variance because it's a positive term. So now we have this B times the regression of phi j on phi I, okay, minus C. And now with this extra term. This extra term is another regression, but now it's the regression of the product with on phi I, okay? Which is a weird thing, right? Because in some ways it's a weird thing, right? Because it's the regression of the product of the phenotypes on one of the phenotypes, right? This is a bit more easy. This is a bit easier to understand because it's the regression of the partner's phenotype on the self phenotype, right? So if it's how much, if you change the self phenotype from 0 to 1, how much does the partner's phenotype change, essentially? This is how much does the product change if you change it from 0 to 1, okay? Obviously, when the product can only be 0 when your self phenotype is 0, right? If you go to 1, though, it's not going to, it can be 0 or 1, right? Because it depends on your partner's phenotype, right? So, so this covariance term is different than this covariance term. And sometimes people call this like triplet relatedness, because in some models, it just basically ends up being the corresponding to probability that 3 individuals are have the same type. But it's a different quantity, and we're going to see that quantity now becomes frequency dependent. Okay, this beta becomes frequency dependent, and but before coming to that, we can still write down. We can basically write down this B times this R So then Hamilton's rule becomes B times this first regression coefficient, which we called relatedness before, right? Minus C plus D times now the second regression coefficient greater than 0, right? So this is another version of Hamilton's rule effectively. Okay. It's not just B times R minus C, but there's some other additional term D. Okay. But so what does that term entail? So so to do that, let's just like go ahead and calculate these things. Okay, so this regression coefficient, first of all, this regression coefficient. So okay, I should write delta bar is positive if and only if this is positive. So this regression coefficient is simply the covariance, right? I mean, it's defined as the covariance of the product with phi I over the variance of phi I. Okay. So let's just calculate these covariances. Okay. So now to do that, we need to actually look at what the population is. So suppose the population is genotype 1. So the frequency of the population, the genotype 1 in the population is, so frequency of genotype 1 equals P. Okay, so P is the fraction of individuals who are cooperators in the population. Okay, and then, and now we have to actually, to be able to calculate this covariance, we actually have to specify, okay, how do individuals interact, right? So far, we got away with not making any assumptions about that, right? Because, I mean, we said this beta is our relatedness coefficients, but we didn't say anything about where that beta comes from, right? We didn't say anything about where the covariance of the J of phi J on phi I comes from, okay? So now we have to actually say something about that. If we want to actually calculate that covariance, we have to say where it's coming from, okay? Otherwise, we don't know what generates the covariance. We don't know what it is, right? So now, and there are actually, and okay, so down, and here is where you can spend, 20, 40 years of your life writing and reading papers about different population structures and different sort of life histories and so on, and calculate these covariances, these regression coefficients or relatedness coefficients and so on. And people have done it. We're not going to go into detail of that. We're going to use sort of like the lazy man's version of population structure, or what someone once called the Mickey Mouse version of population structure. Okay, so we're going to just assume that a very simple model of assortment. And the simple model of assortment is if you have an individual of type A, right? That individual with property R, small r, interacts with another type A, and with property 1 minus R, interacts with someone at random from the population. Okay, so this is a simple model of assortment. Okay, and Mickey Mouse. I don't actually. It's a very cartoonish model, right? We don't know. I don't want to talk about like what generates R or so on, but somehow there's this mechanism, right? Where with probability R, you pick someone that's exactly your own type, okay? And it could be that with probability R, for example, you interact with your sibling, right? And your sibling in this model, because we ignore mutation, right? Your sibling will have the same genotype as you do, right? In the haploid model with no mutation, if you have a sibling, that sibling is exactly identical to you, right? So that could be the case, right? So R could be the frequency of within family interactions, and 1 minus R could be the frequency of you go out and meet someone at random, okay? But whatever it is, that's how the assortment works, okay? So these two numbers actually let us write down the frequency of different pairings. Okay, so you have the frequency of A. So actually I call them 1 and 1. Actually, right? Call them 1 and 0. So genotype 1 interacts with genotype 1 with probability R, and with probability 1 minus R, it interacts with someone at random, which is going to be with probability P. I mean, in this case, actually, with probability P, it's going to be another 1 because that's the frequency of genotype 1 in the population. And with probability 1 minus P, it's going to be a 0. Okay. So and similarly, you can write down if you're zero, if your own genotype is 0, with probability R, you interact with another 0. With probability 1 minus R, you interact with someone at random. And then that's going to be, with probability P, that's going to be a 1. And with probability 1 minus P, that's going to be a 0. Okay. And you can actually write down sort of what the pairs are going to be. This is going to be a 1-1 pair, right? And this is also going to be a 1-1 pair, right? So this event will lead to a 1-1 pair because this is 1 and this is 1, right? This event is also going to be a 1-1 pair. This event is going to be a 1-0 pair, right? Likewise, this is going to be 0-0. This is going to be 0-1. And then this is going to be also 0-0. Okay. And so then you can write down the pairings, so the frequency of the pairings. Okay. So there's the 1-1, there's 1-0, there's 0-1, and there's 0-0. Okay. And these frequencies are now ordered, right? Because we're going to write down the fitness of the focal individual, right? So we want to actually write down, we actually want to know the type of the focal individual. Okay. They're ordered, but they still have to be self-consistent, right? So the frequency of 0-1, 1-0, so all these frequencies have to adapt to 1 basically, right? And the frequency of 0-1 and 1-0 pairs should be equal to the frequency of 0-1 pairs, because obviously each 1-0 pair viewed from the other direction is 0-1, right? Okay, so these are the frequencies. So 1-1 pairs come about when focal individuals that are 1, which are with frequency P, which occur with frequency P, because that's the frequency of the 1 genotype. They either interact with their own type, which happens with probability R, or they interact with someone at random, which happens with probability 1 minus R, and that random individual happens to be 1. Okay, so it's the probability that this happens. Okay, so this happens with probability P. I mean, if you want, you can actually have another decision tree here, right? So first you choose one individual, the focal individual, and with probability P, it's a type 1, and with probability 1 minus P, it's a type 0. Okay, 1 minus P. And then with probability R, that 1 will interact with another 1 with probability 1 minus R. So you get that R here. With probability 1 minus R, that 1 interact with someone at random, and with probability P, that's going to be another 1. So you get 1 minus R times P for this frequency. So 1-0 is going to be P times, conversely, 1-0 is first you choose 1, and then the only way you're interacting with a 0 is if you don't interact with your own type, which happens with probability 1 minus R. And then the probability that it's going to be a 0 is going to be 1 minus P. So 1 minus R, P times 1 minus R times 1 minus P is the probability of a 1-0 pairing. The probability of 0-1 pairing is first you have to draw a 0 individual as your focal individual, which happens with probability 1 minus P. And then the only way the partner is going to be 1 is if you follow this random route, right? So with probability 1 minus R, you selected someone at random, and that someone is going to be type 1, which happens with probability P. Okay, and now you can actually see that these two probabilities are the same with each other, same as each other, which is good because that makes the model self-consistent. Okay, and then likewise, finally you get with probability 1 minus P, you draw a focal individual that's 0, and then with probability R, that interacts with another 0 individual, and with 1 minus R, that interacts with someone at random, and with probability 1 minus P, that individual is a is a 0 as well. Okay, so these are the frequencies of each of the pairings. Okay, so now you can write down. Okay, so what do we want? We want to calculate this covariance, right? so this covariance is, so covariance of phi I times phi j. Actually, let's actually calculate just the covariance of phi j and phi I. Okay, so covariance between the partner and the focal phenotype. Okay, so so remember the covariance. You can write down either the expectation of the product of the differences, or you can write it down as the expectation of the product minus the product of the expectations, right? So so this is all obviously going to be P, and this is also obviously going to be P, right? Because they're both basically just frequencies of the one type, right? So now this product, the expectation of the product is, so with probability, so this product is going to be 1 only if both of them are 1, right? And it's going to be 0 in all of these cases, right? So the expectation of this product is simply the probability that you get this pairing. That's it, the probability that you get that pairing, right? So this product is simply P times R plus 1 minus R times P. Okay, actually, sorry, and I actually made a mistake here. This is not obviously P. You should have told me. Or maybe it is obvious to be. Well, let's see. I think it is obvious to be. Yeah, it is obvious because it's the if you actually add, so this is 1 here and here, right? And if you add these two, and it's 0 here and here, so the only contribution to this expectation is P times R times 1 minus beta, P times 1 minus R times P, and this actually should be, now I'm realizing this actually should be 1 minus R here. Not 1 minus P, because 1 minus P, we already have it here. So, let's just write it out. So this is, but this is clear, right? So the reason that this here is P times R plus 1 minus R times P is clear, because this product is only going to be 1 if both of these, if the pairing is 1, 1, right? Because it's phi I times phi j. If any of these phi I is a 0, phi I or phi j is 0, that's going to be 0. So therefore, the only thing that contributes to this expectation, which, you know, if you write it out, is 1 over n. Doesn't matter what n is, but it's just a constant, times n times the frequency of this pairing, frequency of 1, 1 times 1 plus n times frequency of 1, 0 times 0 plus, and so on. Every time, every one of them will have a 0 term, right? Every one of the other things that will have 0 terms, so they will not contribute. So the only thing that's so this is going to be 0, this is going to be 0, this is going to be 0. So the only thing that's going to contribute is this first term. Obviously, these n's will cancel, and the frequency of 1, 1 is what this expectation is. Okay, and obviously the frequency of phi I is the expectation of phi I is just going to be the frequency of the ones, which is P. Okay, so then the frequency of phi j, I managed to convince myself, but that's the same thing. So frequency of phi j is phi j is only going to be 1 in these two pairings, right? So it's going to be the sum of these two pairings. So P times R plus 1 minus RP plus 1 minus P, 1 minus R times P, okay? So you have P times 1 minus R times P here, and 1 minus P plus 1 minus P times 1 minus R times P here. So that's going to sum up to 1 minus r times p, and you have p times r plus 1 minus r times p, which sums up to p. Okay, so if in doubt, write it out. Okay, is not my general motto. Sometimes I confuse myself when doing these computations, but if you know how to write this out, you can always verify your result. Okay, so this in fact is equal to p, obviously. For a second it was not obvious, but now it's obvious again. Okay. Right, so then, okay, so then this covariance becomes p times r plus 1 minus r times p, okay, minus p squared, okay. And then the variance of phi I, because we are calculating, we are calculating this regression coefficient, right? So it's the covariance divided by the variance. So the variance of phi I is simply p times 1 minus p, okay. And that's, I mean, you can actually write it out if you want yourself by writing out the covariance of phi I and phi I, but or you can just remember phi is just a binomial variable, and its variance is p times 1 minus p. Okay, so then you can write down the covariance over variance is you got so the regression coefficient beta phi I, phi j, phi I is the numerator is this covariance. I'm going to factor out p, r plus 1 minus r, p minus p, okay, from this p square divided by p or p times 1 minus p. So now you got, there's a minus p here, there's 1 times p here, that cancels. There's a minus r, there's an r here and then minus rp here. So this becomes 1 minus p times r. So then there's a 1 minus p times p, p times p, p times 1 minus p. So this becomes r. Okay. So this is how that regression coefficient of the partner's phenotype on the self-gene phenotype becomes equal to this assortment coefficient r. Okay, in the simple sort of cartoon model. Okay, that's where in the sort of the Mickey Mouse model, that's where r comes from. Okay, and rb minus c. Okay, all right. So then let's do. Okay, so this is a simple case. This was a simpler regression coefficient, right? So now let's do the other regression coefficient, phi I times phi j on phi I. Okay. And again, this is the covariance of phi I times phi j with phi I divided by the variance of phi I. Okay. All right. So this covariance. Okay. So this covariance of phi I, phi j, phi I is the expectation of phi I, phi j times phi I. So the expectation of the product, which is phi I squared times phi j, minus the product of the expectations. So now this is why it's good that we calculate this thing, because so now this is p, we know before, and we also calculated this now, right? Before, right? Simply this term, right? So this is p times r plus 1 minus r p, right? So now what is this? This is, I'm just going to write this as e to expectation of phi I squared, phi j. Okay. So again, expectation of phi I squared is times phi j is only going to be 1. It's 0 whenever phi I or phi j is 0, right? Because it's a product of phi I and phi j, right? So this is only going to be 1 in this pairing again. So that expectation is still on, and then its value is going to be 1. So that expectation is still going to be only this frequency of this pairing. Okay. So this actually happens to be exactly equal to P times R 1 plus 1 minus R times P. Okay, so now this covariance is covariance of the product with the focal individuals phenotype is 1 minus P times 1 minus P times P R plus 1 minus R P. Okay, and the only thing I did, I mean, I just skipped a step. This because this term is the same as this term, and this has a P in front, and this basically has a 1 in front. So you can factor out this term, and then you get 1 minus P in a parentheses. Okay, and now again, this obviously is also still P times 1 minus P. Okay, so now if you divide this covariance by P times 1 minus P, you just get rid of P times 1 minus P in front. So then this beta, phi I, phi j, phi I is R plus 1 minus R times P. Okay, so now our Hamilton's rule, which is all the way up here, right, with non-additive interactions. So this thing is R, this beta is R, and this beta is R plus 1 minus R times P, right? So now our Hamilton's rule is B times R minus C plus D, R plus 1 minus R times P greater than 0. Okay. So this is called, this is basically Hamilton's rule with non-additive interactions, non-additivity, additivity. Okay. Okay. The main thing to notice here, the really important thing to notice here is that this addition of this D term coming from the interaction makes us get stuck with this P. Okay, P, remember, is the frequency of cooperators. Okay, so if D was 0, if the interaction was additive, if we didn't have that D term, right, then we know cooperators, whether cooperators will increase or decrease regardless of their frequency, right? Because it only depends on R, B, and C, okay? And those are just constants, right? But whenever D is not 0, it could be positive or negative, then there's this P term here. So it's possible that for some frequencies, cooperators will increase, and for other frequencies, cooperators will decrease, okay? And in particular, so in particular, this is, so R is between 0 and 1. We introduced R as a probability, right? So it has to be between 0 and 1. So 1 minus R is a positive term, right? So, so then you have P times some positive number times D here, okay? So if D is positive, then this condition, the left-hand side here, this condition will be increasing in P, okay? So if you call this sort of the inclusive fitness effect, okay, or just IFE, inclusive, I mean, it's actually, I don't know if you would call it that. Most people would call it that because it's not RB minus C, but that's typically what people call inclusive fitness effect. But if maybe I should just call it the left-hand side here. Left-hand side, which is this term, right? So as a function of P from 0 to 1, okay, it's going to be decreasing. It's going to be decreasing if D is negative, and it's going to be increasing if D is positive, okay? And depending on, okay, so maybe I should do different graphs. So if D is negative, then for lower values of P, for low values of P, this thing could be positive, right? The right-hand side could be positive, in which case P would increase, right? Because this is the condition for cooperators to increase, for delta phi bar to be positive, right? So in this case, cooperators would increase. But for high P, cooperatives will decrease, so P will go down. Okay, so that's when D is negative. That means that there's going to be a sort of a mixed equilibrium, right? There's going to be a P value where if the population is below that P value, cooperatives will increase. If the population is above that P value, they will decrease. Okay. Whereas if so this is with D negative. Okay. Whereas if D is positive, okay, then you're going to get something like this potentially, right? By the way, I mean this doesn't have to cross 0 between 0 and 1. This can be completely above the line or below the line, but interesting cases are when it crosses 0 between P equals 0 and 1. So in this case, if cooperators at already high frequency, right, then the left-hand side of this equation of this inequality will be positive and cooperatives will increase further. But if the cooperators are at low frequency to begin with, then the left-hand side will be negative and they will decrease, okay? So in this case, there's sort of bistability, right? P equals 0 and P equals 1 are both stable, okay? So this is a mixed equilibrium, and this is a bistability condition. Okay, some P between 0 and 1 will be mixed equilibrium, and in this case, P equals 0 and P equals 1, both stable. Okay, and it depends on the sign of this synergism coefficient. If the synergism coefficient is positive, then you get positive frequency dependence. So this is called positive frequency dependence, and this is called negative frequency dependence. Okay, and in fact, if you think about it, this is and this basically takes care of every type of evolutionary game, 2x2 evolutionary games you can think of. Okay, because I mean, we started out with this donation game, with this additive Pearson's dilemma or donation game, and then we added this D. But it turns out any game for evolutionary dynamics, any game, any type of games, with symmetric game with 2 strategies, 2 individuals and 2 strategies, right? You can basically sort of normalize one of the payoffs to 1, okay, and express all the payoffs as a function of relative to that payoff, okay, and then you only need 3 numbers, okay. So you need 1 number for each of these other cells, okay. So therefore, and then once you do it like that, once you express it with this formulation, you can just plug it into here, okay, and you know, if you have this sort of a certain mechanism, right, and you can get the selection, the direction of selection from this. Okay, I think this is all the time we have, more or less, but I'm happy to take some questions now, or clarify some things if things were not clear. Okay, well, if there's no other questions, then I guess that's where I stop. I hope this was helpful. There's a lot more to be said about social evolution, obviously, but hopefully this gives sort of a basic framework and an introduction to how these models are built and what people are talking about when they talk about Hamilton's rule and additive games and non-additive games and so on.